Hello, everybody, and welcome to today's webinar presentation, How to Use Time Series Data to Forecast at Scale, brought to you by InfluxDB. I would like to introduce you to our presenters. Marcello Tomasini. Marcello holds a PhD in computer science from the Florida Institute of Technology. He has several papers published in international peer-reviewed conferences and journals in the areas of mobile sensor networks, human mobility modeling, and machine learning. He currently works as senior data scientist for Veritas Technologies, where he designed and developed the system reliability score and the storage forecasting algorithms implemented in Veritas Predictive Insights. Our next presenter is Thom Crow. Thom lives in Tulsa, Oklahoma with his wife and daughter. When not helping to connect and build the Influx community, he enjoys writing, podcasting, cooking, and spreading his somewhat unhealthy Christmas obsession with everyone.
All right, thank you, Chris. So here we are going to talk about how to use time series data to forecast at scale, and specifically regarding the use case we had at Veritas regarding time series forecasting. So this is the agenda for today. I will talk a little bit about basic concepts of forecasting. Then I will take a small pause, so if anyone has a question, can ask a question. Then I will explain the use case we had at Veritas and introduce and tackle the challenges of forecast at scale regarding model selection, validation, and backtesting, and finally how to keep the model up to date. Okay, so without further ado, let's start with the forecasting 101. So what is forecasting? Forecasting is the process of making predictions. So we are trying to give an educated guess of the future. Now that does not mean we can actually predict the future. What we do is sort of doing better than just a random guess. And the utility of our model is proportionally related to the accuracy of the model itself and the specific use case. There are use cases that are useful only if they are very accurate. There are other use cases that even like 50% error will be acceptable. Let's take, for example, weather. If we are trying to predict the weather for 7 days, well, the accuracy at the 7th day is very low. So what can be forecasted? It strongly depends on if we understand the factors that affect the data we are trying to forecast, and if that data is available. And also there is a very strong assumption in any forecasting model where we assume that the past data is indicator, so it's a predictor of the future behavior, which means that the way the process that was generating that data behaved in the past will continue to behave the same in the future. Okay, now there are several type of models to do forecasting, and there is pretty much two main type of models. The explanatory model is the one that often we see if we try to apply actual machine learning. So we have a lot of features, and then we try to use those features to give a prediction for a specific horizon. In these equations, the horizon is h, which is how far in the future we are going to forecast. And the other big set of models are the time series models, and those they take in account the past observations of the quantity that we are trying to forecast to do the forecast for the horizon. And time series models have been a lot more popular than explanatory models simply because they are more simple. So they are simple because they only use past observation of data, and also because when we are trying to construct those features to do the forecast, we might not have that data available for future observations, and that limits the usefulness of exploratory models. Another concept that is very popular when we are analyzing time series data is trend and seasonality. And usually, if we take our original data in this graph is at the top, what we do, we extract the trend, which is like it could be positive or negative trend, so it's pretty much going up or going down. And then if there is any recurrent pattern, and that is called the seasonality. Seasonality could be daily, could be weekly, could be monthly or annually. If you think about like a sales cycle, the sales cycle definitely has a annual seasonality and probably monthly seasonality. And then once we extract the trend and seasonality from our data, they remain there. So our residual should be pretty much normally distributed and without having any correlation, autocorrelation, which it means that given the past observations, we shouldn't be able to correlate to future observations. Otherwise, it means that we still have information left in our data. Okay, so I will pause now. If you have any questions or concepts that are not clear, please ask. All right, I don't see any questions, so let's move forward. Okay, so Veritas Technologies. Why we use forecast at Veritas Technologies? Veritas Technologies is a data management company. It is leader specifically in data management and backup and recovery. In fact, Veritas was a big company, a lot more popular in the 90s. Then it got acquired by Symantec, and only recently in 2014 they split again. And still, Veritas products are used by a large amount of customers in the Fortune 500 and Fortune 100. In fact, regarding data center backup and recovery, so any type of enterprise backup and recovery products, Veritas has been leader for 15 years straight, which is pretty impressive. Now, one of the products that Veritas sell is called Net Backup Appliances, which is a hardware version of the Net Backup software. Net Backup is the software that is being used to do data center backup and recovery. And these appliances, they are just pretty much servers with a lot of disks. And the good thing is that these appliances, they report a lot of telemetry data. In fact, we have more than 10,000 of these appliances reporting daily across the world. And so we decided to create an internal software as a service platform, which we call Predictive Insight, to provide our support organization with a tool to gain insights on the whole appliance fleet and mainstream the support process. Specifically, we are trying to move from a reactive type of maintenance to a proactive maintenance where algorithms, they tell us before something bad is going to happen to these appliances so that our support engineers can reach out to our customers and resolve those issues. And part of the telemetry data is regarding the storage consumption. These machines they have a pretty complex configuration. They have a different type of partitions. So they have like deduplicated storage, encrypted storage, raw storage, and like system and logs. And these partitions are statically defined when the machine is configured. So we are trying to avoid running out of storage beforehand. And with more than 2 years of data, and 1 point reported every 15 minutes, we end up with like more than 5 billion data points regarding storage consumption. And therefore, we decided to solve this use case by forecasting the time series data regarding storage consumption, which has several use cases for Veritas that are useful for Veritas. Definitely for resource planning, we want to forecast if we are going to run out of storage within the 3 months, so that the backup admin can reconfigure the partitions if needed. There might be workload anomalies. We observed in the field, for example, ransomware. And often these ransomwares, they delete a massive amount of data at once. So like in our case, for example, if the forecast suddenly exhibits a large error, we might infer that there is something strange going on the appliance. There are issues regarding unavailability and service level agreement, specifically if the partitions, they reach like over 80% consumption, performance degrade, and if the backup fails to finish or does not finish in time, then we potentially encounter a situation where we could have a data loss, which is what we are trying to avoid by doing a backup. And finally, the information regarding the availability of storage is used by our sales organization to reach out to customers and try to sell more storage capacity. So how the storage data looks like? Well, it's pretty simple. It's a time series. We could think about it like a time series for each partition type. And this time series data is the input of our storage forecasting algorithm. And the forecast is then used by other algorithms to provide a numerical score to assess the status of the storage subsystem. And finally, this numerical score is integrated into the system reliability score to provide a aggregated system level score. So this is sort of how the UI looks like on our internal tool. So we have like for each partition, we can see the storage being used and the trend. Now, the fact is we have more than 10,000 appliances, and each appliance has a different partition. So in order to run the forecast, daily forecast for all of these appliances, we need more than a single machine to compute the forecast. So we actually built a whole machine learning platform. This machine learning platform is based on Kubernetes. Kubernetes is our compute farm and resource management infrastructure. We have a microservice type of architecture. So each container actually runs a ETL or machine learning process. And the scheduling and the workflow of our ML pipelines is administered through Apache Airflow, which is a popular tool to manage this type of workflows in several other machine learning platforms, for example, in Airbnb and even Lyft. And then we have our backend infrastructure with a storage based on MongoDB and ArangoDB, which are document-based storage, and InfluxDB for all the time series data. So why did we choose InfluxDB for time series data? Well, time series data is very different from other type of data, and mainly there are requirements of high throughput and high performance that they often are not required for other type of workloads. And specifically, since we are recording a large amount of data points, it's very easy to consume a large amount of storage. And then when retrieving that data, again, we are moving around a lot of data. So in our case, we also using InfluxDB not just for the storage. We have also time series data for CPU usage, for disk IOPS and network IOPS and other stuff. And it is being used not just by the storage forecasting, but we have like anomaly detection algorithms and other type of algorithms. And finally, InfluxDB is also used to serve the REST API. So we have a REST API which is queried to return the time series data for the UI, as I showed before. Now, since InfluxDB is a time series database, it also deals with the queries regarding time series data more naturally than other databases. For example, MongoDB in version 4, they claim support for time series data, but if you look at their how-to, you will actually discover that the queries are exceptionally complex, which obviously hamper the productivity of the team. And then InfluxDB has a very sophisticated indexing structure, which provides high performance, which are really hard to achieve by using other non-domain specific databases. And finally, there is a open source version of the high availability setup, which is useful for production instances, so that even if one of the cluster instances go down, the database is still available. And there is also a very nice API, specifically our machine learning algorithms. They are all implemented using Python, and the Pandas library. Now, if you are familiar with Pandas, it offers a lot of functionality. So being able to retrieve the data straight from Influx to a Pandas data frame makes the workflow a lot easier. Now, this is the setup that we use in our Influx. So as I said, we use a cluster setup for high availability. We use this InfluxDB relay, which is this open source software that provides the HA setup. And specifically, we want to use the community supported fork of this InfluxDB relay because it's more up to date. And pretty much what happens is there's a load balancer that we are running on one of the two nodes of Influx, and the load balancer relays the queries, so any read query to both instances and write to both instances at the same time. So this type of setup not only has that provides HA, it also provides an increase in read performance, so increase in throughput. One thing that is very important in our setup is that InfluxDB relies on high IOPS performance. So we used SSDs that guarantees high IOPS. And also we use instances that are optimized for memory more than CPU. And that is because the way the index works in Influx requires or performs better when a lot of RAM is available. All right. Now we have our setup. We have our algorithm, our setup to run the algorithms in a distributed fashion. The problem is time series forecasting usually is a manual process, and as I showed before, the time series decomposition, it's really hard. You have to test that the residual are normal, and you have to test, the type of seasonality and the trend and so on. And this type of process cannot be done by hand when you have to forecast thousands of time series per day. So it has to be automated. And not only that, once we have the model, we need to evaluate the performance of the model before deploying it in production. Otherwise, we might deploy a model that is not performing good. And then once the model is in production, we have to keep monitoring the performance of the model. And if the model degrades, then we need to update or create a new model. So how do we achieve this automation, and how do we do without a manual intervention? Okay, so let's move to the model selection. So first of all, we need to select a model that requires little to no intervention. And this is because in time series data, there are a lot of issues to tackle. For example, we might have missing values, we might have outliers, change points, and as I said before, trend and seasonality, and also each algorithm has a set of parameters that is called hyperparameters, which we have to choose in order to optimize the performance of the algorithm. So in order to deal with missing values, the normal action is to do data imputation, which is filling in the missing values. And that works pretty good when the data has only a few missing values. Problem is with the type of data we deal with, we might have a lot of data points missing in a continuous time frame. That is because might be that the appliance stops reporting for some time. Also, we might have outliers. Outliers are points that are far from the behavior of the other points, and the normal approach is to just remove them. But if we want to remove them in an automated manner, now we have to have an outlier detection algorithm that can detect those outliers without supervision. Then we have trend and seasonality. We can do the composition, but what about the seasonality period? I said, like, it could be daily, could be weekly, monthly. How do we find that? And there could be multiple seasonalities at once. And finally, when we even if we identify the trend, it might be that time series is not just increasing or monotonically increasing or decreasing. It could have a change in trend. And how do we detect that? And finally, we have to choose the parameters of the model, but that we have to do it for thousands of models. So in the end, we settle on this Facebook Prophet model, which is a easy to understand decomposable time series model. It has three components. One is the growth, which model the trend. Then there is a component S for the seasonality, a component H for the holiday, which can be used to model known periods where you could have outliers, and then the error term. And the good thing of this model is that it is very flexible on the definition of the growth. It could be both linear or logistic, so with a saturation effect. And the seasonality uses a Fourier method which extract any type of seasonality automatically. So we don't need to know the seasonality a priori. And another very useful feature of this model is that it does not matter how many points are missing, and we'll fit the points, whatever points are available, as long as the missing data points don't happen always at the same time. We'll still end up with a reliable model. Okay, now we have a model. So now, how do we evaluate the accuracy of a model? In time series forecasting, the cross-validation is different than a problem like, for example, classification. There are mainly two types of cross-validation for time series. One is called expanding window validation, where we have like the available historical time series data, and we select a initial window we do the forecast, and then we keep increasing the training data and do the forecast and compare against the actual historical data, so we can get the accuracy metrics. This model of validation works well when in our forecasting model, more data is better. So we try to use all of the data available. And that might not be the case for all the models. There are reasons to not use that, where sometimes more data is not better, and we might want to use a fixed amount of data to train the model. And that might be because the type of data is changing, slowly changing over time, the type of process that is generating that data. And in that case, a sliding window backtesting is a better estimator of the performance of our model. Now, if we run this type of process for a lot of time series and for a lot of models, we might get like a sort of a global picture of the performance of our system. So, for example, here was like on a test run. We have for each horizon and for each partition type, given a specific amount of training data here we call sample periods, we generated several metrics. Like, for example, the mean absolute percentage error, or the coverage, which is how much of the data falls within the confidence interval. And I suggest to check the papers linked in the slide. They are very useful to study those type of metrics and why one metric might be more suitable for a specific use case than another one. And that's why we also generate multiple metrics. Okay, so we have a procedure to test our algorithm. The problem is we have, to Veritas, we have more than 70,000 time series. And we have to run this process for all of those or for a subsample, and run this iteratively for maybe 2 years of data. And this type of process takes a lot of time, and therefore we are always running behind when we are trying to evaluate the performance of our model. It becomes like a type of batch process, which might be run like once a month, and that is not what we want. We want to be more up to date. We want to react to changes in a faster manner. So one thing would be to have the error as a time series data. So how do we create, or how do we engineer the system so that we get like the measurement, a continuous measurement of the error of the forecast? So we came up with this simple solution. We can save all the past forecast data, and we forecast not for a specific horizon, so not for a specific time in the future, but we do it for multiple horizons. So, for example, 1 day, 7 days, 30 days, 90 days. And as we generated this forecast, we compare against the incoming new historical data, so we can compute the error over time. So once the system it is running, it will start generating also the error measure. And with this setup, we don't need to do all the computation at once. We can just do it for only the new upcoming data. And it is also useful to do A/B testing, where we deploy a new model in parallel to the existing production model, let it run for some time, and compare the time series data regarding the accuracy, and to see which one is performing better. And also, since we have measuring the error rate online, we can also add alerts or use the error data for example, anomaly detection type of algorithms. So in order to support this type of functionality, we had to engineer the data in Influx. So the first step was to create one measurement for the historical data and one measurement for forecast. In Influx, a measurement is pretty much can be considered a collection or a table in other type of databases. And in Influx, we also have two concepts. One are the tags, and another one is the fields. Tags are indexed fields, while fields are just numerical. And with this type of setup, we could potentially support a use case. The problem is when we in a measurement, when we have a lot of time series, the amount of memory consumption by InfluxDB increases exponentially. Therefore, this type of approach on using just two measurements doesn't really work. So we moved from two measurements to one measurement for each appliance. So in our case, more than 10,000 measurements. And each measurement contains both the historical and forecast data by just adding a Boolean flag in the tags. With this solution, we can scale very well. Pretty much we can scale indefinitely, and it's very useful also for when we want to do data sharding. A problem is now we don't want to retain the forecast data for a long amount of time, simply because we are generating the forecast every day. So, and for multiple horizons. So by the end of like a short amount of time, we will have a lot of data just coming in from the forecast and not the historical data. So we want to be more efficient on the storage from a storage point of view, and therefore we had to implement ad hoc queries that do the cleanup differently from the retention policy that is used on the historical data. Now for the accuracy data, so the layout, the data layout for the online error measurements, again, we started from one measurement. That is very useful when we want to do analysis for the whole appliance fleet. And here is very useful having like in the tags, a tag horizon, so we can do a group by on the horizon and generate that type of graphs that I show beforehand. But again, given the number of appliances and the number of horizons that we're going to generate, we encounter the same issue with the cardinality. So we moved to, again, to one measurement per appliance, which, yes, scales well. Now, the type of cross analysis that I showed before, it becomes really hard. You have to gather the data from all the measurements, and then once you have the aggregated data, we can generate the appliance fleet level type of analysis. But that's sort of okay because this type of process can be sort of automated by having a ETL process and then store it maybe into Hadoop cluster, and then from there we can generate our reports on a fixed cadence, like once per month. Okay, now there is also another issue that we have to track for when we have the error measures. We have to track which model generated those values, and it is important because it's not just the type of model that generated the error metrics. It is also how the model was configured, so the set of hyperparameters that were used for that specific model. And That is important because, as I said before, we might want to update the model because the model is not performing good anymore. So we need to track what is performing good or not, and if anything, update it. And the problem again is the same as when we are doing the forecast. We have thousands of models, and we need to tune all of them one by one in an automated manner. Not only that, these models, they change over time because the data is slowly, the process that is generating the data is slowly changing. And we can't really do backtesting just to get the set of hyperparameters every time we need to update a single model. So instead, we use a advanced mathematical technique, which is more efficient. This technique is called sequential model-based optimization, or Bayesian optimization is also known as, where we are trying to minimize our objective score. The objective score is nothing but our error. It could be the root mean square error, so it's one type. It could be our mean absolute percentage error. So depending on which metric we decide to optimize for, then we will try to minimize that error rate. And then we build a probability function of this error and try to estimate the set of parameters X that will minimize the objective score. And also we have to come up with a selection function that select the set of hyperparameters to try in the next iteration of this process. So how does it look like? Actually easier than it sounds. We start with a randomly chosen set of parameters for our model, and we run the model and measure its error. And we will see that for some set of parameters, the model will perform better, and for some will perform worse. So when we pick the next set of parameters, we choose parameters that are closer to the ones that perform better. That is, that they minimize the error. And after some iterations, we will end up with a set of parameters that in fact minimize the error of the model. Now, in order to support this type of functionality in our system, again, we augmented the accuracy data layout we introduced before. We not only have the horizon, we start adding a model type tag and a hyperparameters tag. And the problem is, specifically for the hyperparameters setup, is that some models, they have hundreds, possibly thousands of hyperparameters. For example, if we think about a neural network model, we might have millions of parameters. And obviously, this type of models and this type of cardinality for the parameters cannot really be stored as tag. And therefore, we switch to a new data layout where all the hyperparameters are externalized. They are not stored inside of InfluxDB. Instead, what we store in InfluxDB is just a reference to a document, and then the set of hyperparameters is stored in one of our document-based storage databases. And in this case, it allows us to, for example, when we are analyzing the accuracy data, we can group by the not only by the model, also by the hyperparameter set. So we can compare even the same type of model with different set of hyperparameters and check which set of hyperparameters is in fact performing the best. So with this, we have a complete setup end-to-end to implement a forecasting system at scale that uses time series data and has both automated forecasting, testing, and it keeps the system up to date without any manual intervention. So in conclusion, we saw that we want to provide a setup that is optimized for IOPS and memory for InfluxDB, that is to achieve the maximum performance. And the HA setup is also useful to increase reader performances, which is important, for example, if you're using InfluxDB to serve a REST API as we do. And we have to pay special attention to the cardinality of the series, otherwise we might encounter memory issues. And with a smart data layout, we can actually scale to thousands of time series data, and while maintaining the ability to do accuracy evaluation and algorithm tuning, as well as doing the type of analytics analysis on like a whole holistic view of the whole data set. Right? So at this point, does anybody have any questions?
I have a quick question. My question is, what solutions were you using before InfluxDB, and what has InfluxDB brought to the table that other solutions did not?
So this platform it's actually been created from scratch, so there was no existing solution before, and therefore we had the chance to take a look at what was available on the market and come up straight with the implementation on InfluxDB. Now we actually evaluated like a document-based type of storage or relational type of databases, and the biggest issue with any of these type of non-domain specific databases is that they really not meant to work specifically on time series data, and therefore you have to pretty much implement a lot of boilerplate code or boilerplate logic to deal with basic operations on the time series data. Operations like a simple group by, for example, they can be fairly complicated. Also, since they are not, they don't take into account how the requirements for time series data, what happens is often to optimize performance, you have to sort of decide the type of aggregation of your data beforehand, and that is especially true for MongoDB. Their recommendation is to create buckets beforehand, and if for any reason the production system changes and is reporting data with a different frequency than it is expected, now you have to literally migrate and re-implement the whole data layout, and that is exceptionally expensive. So when we saw that type of issues that they could come up, we simply went with a domain-specific solution. And InfluxDB in particular, it's very, very easy to set up. You can be like up and running with a Influx setup in less than 10 minutes, and with high performance. And it also has a very simple query language. Now with Influx 2, they are introducing a more advanced query language, but the SQL type of query language is something that most people are familiar with, and it makes the team very productive. We are a relatively small team, so believe it or not, we start from nothing and in less than 1 year, we went with a system that could run at scale for these 10,000 appliances. Okay, I see another couple of questions here. Rahul is asking, can we also try segmented regression combined with dynamic programming for storage forecasting as a time series problem and use Bayesian optimization for hyperparameter tuning? Well, if for segmented regression you mean by like piecewise regression for the time series data, so you have to still identify like if there are like change points. Yes, there are systems that they use they do that, and it is definitely possible. There are like hundreds of algorithms for forecasting. It's just that usually for time series data there are some known type of algorithms like ARIMA models or exponential smoothing, and more recently people start using recurrent neural networks or LSTM deep networks, mainly to have more accurate forecasts. So yes, it is definitely possible. One could do that. Truth to be said, the choice of the model is more to, it depends on the type of data you have and, literally speaking, the performance that the model achieves. So it doesn't matter. You could even just do a simple linear regression. If simple linear regression achieves good performance, then why not? The choice of model is not just to have a fancy model. The model is chosen just to solve the use case. In our case, for storage forecasting, for example, we don't need exceptional accuracy. If you were to be Uber and trying to forecast, I don't know, some the route travel or some pricing type of metric, then you want to be really accurate because even a small error there would cause like millions in damage. Okay, so we go to with Anantasak question, and he's asking, as of data scientists, how we handle and manipulate data in real time from streaming data? In our case, we have yet to have a streaming setup, but if you go out there is a project that is it's very popular. It's called Apache Kafka, and it provides like a streaming type of storage and querying, and from there you could have two main approaches. You could perform like a sort of processing record by record, or you could do something like a mini batch type of processing where you wait for like a fixed amount of time, collect whatever records were received in that time frame, and process them. It really depends on your use case. For alerting, probably you want something like a record by record, and that is very useful if you are in the AWS domain. You could attach like a Lambda function. If you are into machine learning type of things, probably you want to do mini batch type of approach, because otherwise it would be too expensive to just run a machine learning algorithm for a single record. And there is a follow-up question again from Anantasak. Having a machine learning tool that self-corrects to minimize prediction and classification error is the challenge. For getting factor, our package could be effective if it is adjusted automatically and more in industrial model. Yes, the R forecasting package is very powerful, but we don't use R at all. So I agree. Most of the production type of or application in production of AI and or data science type of analytics and so on, they are really challenging to be run in an automated fashion. Sometimes it is possible to automate the process because you can, if you have like some reference data, you can check how you are performing as the data comes in. For example, It's relatively easy if you do it for search because you know what the user search and what they click, so you sort of can match what queries are actually useful to the user. It is a lot harder, for example, if you have a image classification process where the user can submit any random image and you don't know if you actually did the classification correctly until somebody goes and manually check that the image, yes, it's a cat image. So it depends on the use case again. And again, for time series data, it is sort of, it is possible because you have the data that is coming in. So the historical data actually is your labeled, so your supervised type of learning. And you can build an infrastructure around it to sort of have this automated process. But that is specifically, that specifically works for time series data. That's not the case for all the machine learning type of use cases. All right. Any more questions? All right. I think that's it.
Great. Thank you so much, Marcelo. I'd like to thank everyone for attending today. I'd also like to thank Marcelo for a great presentation today. And lastly, I'd like to thank Influx Data for providing the audience with a great webinar presentation. And audience, we hope you learned something new that will help you in your developer career. Have a great day, and we'll see you next time.
Thank you, everyone.
Thank you.